Hey, this is Ken the Metal Professor. I came across an interesting problem in one of the mathematics subreddits. It's been hovering there a couple of days, and so it seems like a good time to kind of use it as an example of a broader theme, which is Gaussian elimination. When I've done these videos before, I've done 2 or 3 problems. This one I'm just going to restrict to this one. Anyway, it comes from the Learn Math subreddit, and the question was posed as follows. Well, not quite like this, but the spirit of the problem is to analyze the hell out of the solutions to this given system of 3 equations and 3 unknowns. Now, meaning there's these mystery values A and B in this system, and the idea is to diagnose the system to see what happens with A and B if we want to have no solutions or infinitely many. How can A and B be tuning dials to generate certain results? And as you know, for a system of equations like this, there's 3 expectations. You can have a unique solution, you can have no solution, or you can have infinitely many solutions. And so we are going to dive into Gaussian elimination to get a handle on this information. And so I've built the augmented coefficient matrix for this system, where we just recognize that all the good information is in the coefficients. The fact that the variables are x, y, and z is totally irrelevant, so we don't really need to see them. And so we can arrange the coefficients in a matrix. This is called the augmented coefficient matrix because the coefficients of x, y, and z alone would form a square 3 by 3 matrix, but we need to carry along these right-hand side values as well. So the augmented coefficient matrix isn't square for this system. Now, hopefully you know the rules of Gaussian elimination if you're watching this, but you are allowed to multiply any row by a constant. Multiplying by 0 doesn't really help you out, so let's put that one aside. You can add 2 rows together and replace one of those 2 rows with the result of that addition, and you can just interchange 2 rows. Okay. And usually that interchanging is done for convenience, where you think, ooh, this would be great if this number was up here, and then you can do that. You could just change the rows. But we actually don't have to do any of that for this problem. So the strategy for Gaussian elimination is to clear out everything below the diagonal and then everything above the diagonal if you want to proceed that far. And so our first goal is to clear out the 6 and the 5 using the 2 rules that I just mentioned, or the 3 rules, but we're not swapping rows, so 2 rules. The 6 and the 5 are the targets, and this 1 up at the top is the arrow that's going to shoot them out. Whoever invented this system was kind enough to put 1s in that top row, which is a help. Okay, so in order to take out this 6, what if we were to multiply row 1 by 6, multiply row 2 by -1, add those 2 rows together and put the result in row 2? Or a little bit more concisely, 6 row 1 minus row 2 will go into row 2. Now remember, technically, subtracting rows is not one of the operations that's legal, at least by the book in Gaussian elimination, but this is just a nicer way to say 1 row plus a negative value times the other row. Okay, so we're all friends here, and we will agree we're allowed to subtract things as well. To clear out this 5, we're going to do 5 row 1 minus row 3, put that result into row 3. When we do that, we've cleared those out, and we've updated all the values in rows 2 and 3. You can pause and check those out. But for example, for this first operation here, 6 row 1 minus row 2, if we focus on this entry, we'd get a 6 minus 5b, put 6 minus 5b in that spot in the new and improved, so to speak, row 2. Okay. Now, following with Gaussian elimination, the next strategy would be to take out this entry below the diagonal, this 3, in row 3, column 2. So that's our target. We need to use row 2 to help take out that 3. Because if we involve row 1 and we do some combination of row 1 and row 3 and then replace row 3 with that result, we're going to spoil that 0. So we don't want to do that. So we have to use row 2. One option would be to take row 2 and just multiply across by 1/10 first to put a 1 in this spot, which is more convenient. But then you've got fractions over in these other entries, and that really clutters things up. So one of my recommendations for Gaussian elimination is eventually, if you're going all the way to reduced row echelon form, you would like to have 1s down the diagonal. Make conversion of the diagonal entries to 1s the very last thing that you do, unless like there is a common multiple across the entire row that you can get rid of with multiplying by 1/5 or something like that. Otherwise, just leave the numbers on the diagonal as they are, let them evolve. At the very end, divide by those values to produce 1s in those spots, just to reduce clutter. Now, with that being said, how do we use this 10 to take out the red 3? Well, we've got to find a common multiple, and so that means we're going to do 3 times row 2 minus 10 times row 3 and put that result into row 3. And here's the result. Again, if you want to pause and double check, go right ahead. Now, at this point, we can already look at row 3 and see what it would take for certain values of B and A to produce no solution. If we have in this bottom row 0, 0, 0, and then something non-zero in the far corner, that is an indicator of no solution. The reason being that you have to remember that every one of these rows in this matrix is an equation in disguise. So right now, row 3 says 0x plus 0y plus this value times z equals this value, the negative 32a plus 37. An equation that reads 0x plus 0y plus 0z equals something non-zero, that can't work for any x, y, and z, because that's basically 0 equals something not 0. And so if this term with the b in it was a 0 and this lower corner term was non-zero, we will have no solution. And so you could solve that for what b would make this 0 and what a would we want to avoid to keep this term non-zero. Okay, now I'm going to hold off those details until the end, but I just wanted to point out that at this point we're already ready to diagnose when there might be no solution. All right, continuing with Gaussian elimination, we've cleared out below the diagonal. Now it's time to clear out above the diagonal. So now we want to take out this red 1. Tux, the calculus dog or the linear algebra dog is paying a visit. There he is. He's being annoying. He must want to watch. Okay, you go away now. I don't have any food for you. Go away. There you go. So to get rid of this red 1, again, we have to use this 10 to do it. So let's do 10 row 1 minus row 2 into row 1, or equivalently, we could do negative 10 row 1 plus row 2 into row 1, but that would turn all these other terms into negative values, or introduce negative values. So let's just do it like this. There's the result. Pause and double check if you would like. Okay. The next stop would be to eliminate, if we could, both of those terms in column 3, the upper 2 entries. In a perfect world, we would eliminate both of those to get to the solution. Now here we're going to get roadblocked in a minute here, but if you look, if we say, well, at least we could eliminate this term, conveniently, that term is simply a multiple of its partner down there in row 3. And so if we take 3 row 1 plus row 3, we're going to generate a new 0 that we can plop there into row 1. So 3 row 1 plus row 3 into row 1 puts a 0 in that spot. Now, could we eliminate the 6 minus 5b altogether? Well, yeah, but we'd have to start multiplying both row 2 and row 3 by nastier expressions. We'd have to multiply row 2 by this whole entry from row 3 and vice versa, and then that multiplication would carry over into these other entries, and that would just be gross. So I'm not going to do that, but notice that we can at least eliminate part of this term by doing the following. Oh, wait, sorry, I forgot. I made these slides first. So put that thought on hold. I'm not going to go back and edit this. I'm just going to go with it. Notice that, say, in this top row, there's a common factor of 10, right? And in this bottom row, there's a lot of minus signs. So I've multiplied row 1 by 1/10, and I've multiplied row 3 by -1. That looks a little bit better. Okay, now the story between row 2 and row 3 is that if you look, removing this entry in its entirety is going to make things really messy in the other rows. But at least we can eliminate this term with the -5b if we take 3 times row 2 and add it to row 3 and plop that result in row 2. Okay, so that result will look like this. And again, a little bit more cleanup. Take out a factor of 10 across row 2, and there we go. There's almost a factor of 3 to take out of row 3, except that 37 screws everything up. Okay, but so this is as good as it's going to get for the moment. We could continue and turn this entry into a 0, but again, messy. So let's just leave it there because we can still get at the information that we want to. This is as good as it's going to get. There's only one instance of B left, and all the A's are isolated in the right-hand column. So now we can start analyzing information about B and A across the board. Like I said before, I'm not going to try to put 1s on the diagonal just yet because I don't want to put horrible fractions over here in the right-hand column. At the moment, we're just asking what has to be true about A and B to get certain results. So let's start diagnosing the heck out of this thing. Row 3 tells us that if B is -4/5, we'll end up with a 0 right there. If A is 37 over 32, this number would also be 0, and that's not a problem. That's 0, 0, 0, 0. That's okay. But if this ends up being 0, and this ends up being non-zero, then like I said before, that's an indicator there's no solution. So this is the information that we had in hand earlier, but I just didn't follow it up at the moment. But if B is -4/5, that makes this 0. If A is not 37 over 32, then this term will not be 0. And that row, 0x plus 0y plus 0z equals something non-zero, that can't happen for any values of x, y, and z, and that means no solutions. This same row then, if we end up with a 0 here and a 0 here, that will tell us there are infinitely many zeros, because when we have 0x plus 0y plus 0z equals 0, we now have an expression or an equation that is totally true and totally useless, because it's true for every value of x, y, and z, and so it doesn't help us determine what specific values of x, y, and z we might have, and further, that takes out 1 degree of freedom from our system, and so at best we can only resolve x and y in terms of z, and that means that we have infinitely many solutions. Okay, and as long as B isn't -4/5, we will have a unique solution. As long as this number isn't a 0, we can have anything over here on the right, and we're fine. So as long as B isn't -4/5, we're going to have a unique solution. You know, even if A ends up being 13 halves, then row 1 would say 3x plus 0y plus 0z equals 0. Well, then x has to be 0. So having zeros in this rightmost column isn't an issue as long as we know what's going on here as well. Okay, and so that's sort of the idea. We can to get to this point where we can resolve what information has to be true about A and B to lead us towards the different solution scenarios. All right. If you wanted to go farther and actually get the corresponding values of x, y, and b, well, row 1 tells us what x looks like directly in terms of a. Row 3, if there is a unique solution, row 3 tells us exactly what z has to look like. It would be 32a minus 37 over 12 plus 15b. And then row 2 says 3y plus 3z equals some stuff, which means we can't resolve, once we know z, we can resolve y. The other option would be to go back and continue with Gaussian elimination to put a 0 in that spot, and then row 2 would get us y directly. So those would be your choices. I haven't done this to follow through to get the precise expressions for x, y, and z. Okay. Even in the case of infinitely many solutions, x is still uniquely determined. If this bottom row was 0, 0, 0, 0, then at best we could write y in terms of z. So z could be anything, and then the value of y would be based on z. And that's where you get your infinitely many solutions. Now, when you're solving systems of equations, determinants can also be a tool to do this. So if we went back to the very beginning and just built a regular coefficient matrix, its determinant would be 12b plus 15, and you may know that you will have a unique solution when the determinant isn't 0. And so for a unique solution, we would need b to not be negative 4/5. Now, we also discovered that in the other method. And you might say, well, this is so much quicker. Why don't we just do this? And it is quicker to get to this information. But if the determinant is 0, well, you don't know if the solution doesn't exist or if you have infinitely many solutions. So you can't make that resolution. And to get to what the values of x, y, and z look like in either the unique solution scenario or the infinite number of solutions scenario, you still either need to bust out Cramer's rule, which means 3 more determinants, and that's only good for the unique solutions anyway. That still doesn't tell you anything about the characteristics of infinitely many solutions. So for the case of infinitely many solutions, you're kind of stuck with all the Gaussian elimination. So you might as well just do it from the get-go. Okay, so that took over 15 minutes. That's why I wanted to do only one problem, but I picked on this one because it's a fun story, because going through Gaussian elimination is entertaining. So I hope that helped a little bit. And yeah, I'll put something up again in another couple of